Great. Hi everyone, I'm Premma Makanji. I'm an Associate Structural Engineer at Eckersley O'Callaghan, focusing mostly on refurbishment projects and sometimes listed buildings as well. A bit about EOC. We are a company of about 150 engineers who are spread across 8 offices globally. About 2/3 of those are in London. This is our kind of mission. We're passionate about designing great buildings and enabling a sustainable built environment. What we do is structural and facade engineering. Just going to rush through this quite quickly, but this is kind of the range of projects that we work on. You'll see there kind of a variety of scales and different sectors. And also we work with kind of a wide range of materials, so from the kind of natural and bio-based, for example, timber and stone, but all the way to like engineered and novel materials like glass and acrylic. So these are kind of 3 of our focus areas: sustainability, digital design, research and innovation. And we think that the kind of future of engineering and construction is where these 3 areas meet, and we've been working on some tools that bring these focus areas together. This is a bit of a kind of step back. So this is kind of a graphic from the Institution of Structural Engineers, and it's about whole life carbon. So recently there's been quite a bit of success in regulating energy efficiency by which reduces operational carbon emissions. And in the future we'll be decarbonising the grid, which means there's going to be greater impact from embodied carbon. So this means there's a shift in the importance to structural engineering as engineers specify many of the materials that are going into buildings. So we were thinking about that, and we started to look at reducing embodied carbon in terms of our projects. And we thought that it's at concept stage where we've got the greatest ability to make changes and add value to the design without significantly impacting the cost of the project or the environment. So we've made 3 tools. So 2 of them are based on the early design stages where we need to rapidly explore different options, and 1 is based on the later design stages when a detailed design already exists. So these are the 3 tools. The first one is the smart massing tool, which is made on Rhino and Grasshopper. And what it does is you can put in the geometry of your building, and you can change the structural grid and the frame, and it will calculate the embodied carbon in real time. And then this is a bit about how it works, which is quite easy to show in a video, but basically you can set the shape of your building, set the grid, you can rotate the grid, you can make different bays different sizes, you can see what impact that has on the foundations by adding different number of stories. You can also change the materiality, and we think this helps us to influence the materiality and the grid at an early stage of the design. So the next tool is the Bay Builder, which is very similar to the smart massing tool, but it's for facades. So in a similar way, you can change the kind of bay size and the inner and outer skin of your wall, the type of insulation and the size and shape of the window. And again, you can see in real time what that does to the embodied carbon and also the U value. And it works also for glazed elevations with different kind of size of infills or rain screens. Then the final tool, which is for the advanced design stages, is basically just a Revit plugin. So you would have your structural model, and then you would open the plugin, and it's calculated lots of, so each of your areas is put in, and you can select them, and then it calculates the volume and the density of that material, and then you can assign them a material, and it goes to the database to pull the embodied carbon from there, so then it can calculate the embodied carbon for the whole building. And the main thing to say about this tool is that EOC have made this open source, and it's already been downloaded by about 150 companies worldwide. So on the back of that, we decided that we would calculate embodied carbon on all of our projects. So we've had a look at what the data has told us so far. So these are our projects that we've calculated embodied carbon for over the last sort of 10 years. In each dot represents a project, and the vertical scale is the embodied carbon. And then the yellow and green lines are the rating from the Institute of Structural Engineers called the scores rating, which comes from the LETI targets. And as you can see, the dots are quite widely dispersed. However, the grey line is the trend, and it's sort of on a gradual downward slope. But if we're going to reach net zero in 2050, then we need a much sharper trajectory. So we also plotted all of our projects in terms of size, and also the orange dot is refurbishment and grey is new build. And you can see that it's mostly refurbishment projects that meet the scores rating A. And above that, you have some projects that are refurbishments that have quite a high embodied carbon. And looking into those, a lot of them have basements or large areas of floor that are being replaced. And sometimes quite a lot of load-bearing walls, which are then also included in our model. And then the final graph from that is that all our projects in order. So the main thing that you can see there is that the refurbishment projects have the lowest embodied carbon, but after that, it's the timber ones which score the next lowest. So it was clear to us that we need to be doing more refurbishment. So we've sort of thought about how we can do more refurbishment. So we've put together some case studies that are kind of varying in scale and typically not buildings that you would consider to be like super glamorous and not listed. And this is the kind of like hierarchy for net zero structural design. So the first one is a project that we're doing at Quentin Blake Centre for Illustration. And it's a building that was originally a storage building. It's not particularly high quality. It's actually not in. It's suffered a lot because there are trees directly adjacent to the building that have affected the walls and the entire ground floor slab. On top of that, the roof structure is not very consistent. It's been adapted over time when leaks have come in. So our original design, so the architect wanted to put a two-story building there, and our original design was to replace that building and put a new steel frame on a kind of piled foundation. However, due to costs, we were asked to review retaining the existing building. So we had to take a step back and look at the drivers behind why we were replacing the building, and the main one was the fact that the adjacency to trees were causing movement. So in that point, we worked with the client to directly discuss with them the implications in keeping existing, and that was going to be that there'd be some like minor cracking in the future, and possibly some needing to replace like thresholds. So once they understood those kind of parameters, they were able to accept that. So we moved towards a timber frame. So we built a new timber frame internally, and we were using whichever trusses we could and moving them up to the roof. On top of that, we put in a kind of Victorian-style raised timber ground floor. So that dealt with the bulk of the movement, but not all of it. And this is kind of just a basic example about how you can work with the client to kind of help them understand the engineering parameters, and that means that you can deviate from a kind of standard engineering approach and ultimately kind of make quite a large cost saving as well as a large embodied carbon saving. The next project is our project at London South Bank University. So this is an existing building from the 1970s. It was used as teaching and office space, and had quite a cellular layout, and the proposal was to change that into a student hub with more of an open plan layout, and the intention was to retain existing. The structure itself was a concrete frame with waffle slabs. So our first, the main thing that we did was fully understand everything there was to understand about the structure. So we knew that where there was capacity and where there wasn't capacity. So for example, nearly all the floors were okay, but then a few areas where we were increasing loads, such as plant rooms, we added carbon fibre strengthening to the underside of the slab. And then the other main intervention was that the existing light wells of the building were to be infilled. And we knew that the structure surrounding the light wells didn't have very much capacity, but the columns did. So we spanned the new structure between existing columns at roof level, and then we hung the floors from that structure, which meant that we could take all the load onto the columns and avoid strengthening the foundations. So the outcome of that project is that you can see it's got an embodied carbon of 49 kilograms of CO2e per metre squared, which is about 5 to 6 times less than an equivalent new build. Then the next project is at Magdalen College, is an existing student accommodation, which isn't widely loved by the public as a building. So we were brought onto this project at feasibility stage. On this project, we had very slim archive material. So in this instance, we kind of surveyed the building and helped the architect understand what existing was. So we gave them column locations, downstand beam sizes, thicknesses of slabs. We also used our benchmarking information to tell them what the embodied carbon would be for new build or refurb. And the outcome of this project was that actually the existing building couldn't be retained because the floor-to-ceiling heights were too low and the downstand beams were too detrimental to the servicing strategy. However, in that instance, the footprint of the new building and the existing building was quite similar, so we wanted to have reuse in some form. So we proposed a kind of transfer slab at first floor, which meant that the kind of column locations above could be transferred to the existing column locations below. Then we also proposed building above in timber, so we could do a greater number of stories. And then we could also keep the load within the existing, so that meant we could keep the existing foundations and the existing basement. And then I think I'm running out of time, so I'm just going to flick through this, but this is just a project where we use the smart massing tool to come up with an array of options at feasibility stage to help everyone make meaningful comparisons. I'm just going to leave that. Okay.